Hello, my name is Shahriari, and this is a lecture on linear independence based on my book, Retrolinear. To motivate, let's start with an example. So let's say that V is the vector space R3, the three-dimensional space. S is the set of these three vectors. V1 is 1, 1, 1, V2 is 4, 7, 11, and V3 is 7, 4, 0. We might want to ask, what's the span of S? By the definition, span is just the linear combinations of all the elements in S. Span of S consists of all vectors that you can get by multiplying V1 by alpha, V2 by beta, V3 by gamma, and adding them up. So vectors of the form alpha V1 plus beta V2 plus gamma V3. Alpha, beta, gamma can be any real numbers, including 0. Some of them or all of them could be 0. If you do that, if you multiply V1 by alpha, V2 by beta, and V3 by gamma and add them, what we get is that vectors of the form alpha plus 4 beta plus 7 gamma, alpha plus 7 beta plus 4 gamma, alpha plus 11 beta are in this span of S. If a vector walks through the door and asks, am I in this span of S or not, you would have to say, well, I've got to figure out if there's an alpha, beta, and gamma that I can find that will make you look like alpha plus 4 beta plus 7 gamma, alpha plus 7 beta plus 4 gamma, and alpha plus 11 beta. Just by looking at that vector, it won't be 100% obvious if they're in span of S or not. You would have to do a little bit of work. But you might note that if you add V2 and V3, you get 11 times V1. You can actually solve for any one of them. You can say, well, V3, that means it's 11 V1 minus V2, or V2 is 11 V1 minus V3, or V1 is 1/11th V2 plus 1/11th V3. Any one of them can be written in terms of the other ones. If you don't want to really privilege any one of them, then you might want to bring them all to one side and say that what we have is 11 V1 minus V2 minus V3 equals the 0 vector. The 0 on the right-hand side is not the number 0, it's the 0 vector, it's the 0, 0, 0 of R3, the origin in R3. What this tells us, any one of these equations, is that in spanning, we actually did not need all three. We could get rid of V2 because V2 is already 11 V1 minus V3. So anything that you could have written as a linear combination of V1, V2, and V3, you can already write as a linear combination of V1 and V3. V2 is not necessary. If you were going to use V2, instead of any time you were going to use V2, you can replace that usage by 11 V1 minus V3 and turn that linear combination to a linear combination of V1 and V3. So now we can write span of S in a slightly simpler form. It's things of the form A V1 plus B V3, where A and B are real numbers, and just ignore V2. If we put that together, we get this form, A plus 7B, A plus 4B, A, where A and B are real numbers. And this is much simpler than the one before. If a vector walks through the door, you just look at its third coordinate and say, okay, well, that's A. Based on that, you decide what B is by looking at the second coordinate, and then you check whether or not the first coordinate is A plus 7B or not. It makes life a lot easier. We do not want situations where we're trying to find the span of a set of vectors, and those vectors are linear combinations of each other. And that's where linear independence comes, and now we're ready to define linear independence. So if you have a vector space and if you have a non-empty set S of vectors in V, k vectors in this case, if you can do the following, if you can find k scalars, if the scalars are real numbers, those would be real numbers, such that when you find the linear combinations of those vectors, you get the 0 vector of V. I can certainly find scalars A1 through AK such that A1 V1 plus A2 V2 plus AK VK 0. Why? Well, because I can use the scalars 0, but I want to avoid that. So I want to say that at least one of these scalars got to be non-zero. I consider using zeros for all the scalars as cheating. I'm not allowed to do that. By the way, that backward E means there exists. If there exist scalars, A1 through AK, such that I have a linear combination of my vectors using those scalars equal to the 0 of the vector space, and the added condition that I did not cheat and I didn't use all zeros as scalars. Some of them could be 0, but as long as at least one of the scalars I use is non-zero, yet that linear combination is 0, if that happens, then I say that the set S is linearly dependent. This is for a finite set of vectors. Now, if my set of vectors is infinite, there's infinite number of vectors, then to say linearly dependent means that at least one of the finite subsets of it is linearly dependent. Like this one, that one, that one, and that one. If those are linearly dependent, then we say the whole set is linearly dependent. Now, if a set is not linearly dependent, then it's called linearly independent. And the linearly independent sets are the ones we like, actually. We like independence. For example, that first set that we had at the beginning is a linearly dependent set of vectors in R3. Here's another example. V is the vector space of polynomials of degree less than or equal to 3. I have got 3 vectors, 1 plus x, 1 plus x squared, and x plus x squared. And I want to know, is this set linearly dependent or independent? What I say is that let's try to find scalars so that that linear combination is 0. So that's sort of how I start. I will always succeed. I can pick alpha to be 0, beta to be 0, and gamma to be 0. But that's, again, cheating. If I can find some other set of scalars to make that linear combination equal to the 0, then I've got a linearly dependent set. If only possibility, the only way to make this be true is to have alpha and beta and gamma to be the number 0, then I know that it's linearly independent. So I'm going to find all possible solutions for alpha, beta, and gamma. And if alpha equals beta equals gamma equals 0 is the only solution, then I will know that it's linearly independent. I will write alpha v1 plus beta v2 plus gamma v3, what it is, alpha times 1 plus x, beta times 1 plus x squared, and gamma times x plus x squared. I combine those like terms, multiply it out, and then I ask myself, how is it going to be that this polynomial is the 0 of the vector space? Now, what's the 0 of the polynomial vector space? Is the 0 polynomial. 0 plus 0x plus 0x squared plus 0x cubed. And the only way this polynomial can be that polynomial is if its constant term is 0, the coefficient of x is 0, and the coefficient of x squared is 0. And therefore, what I get is that alpha plus beta must be 0, alpha plus gamma must be 0, beta plus gamma must be 0. So I have 3 equations and 3 unknowns. I use the method from the nine chapters of Gauss-Jordan elimination and solve this. And if you do solve this, you will get that the only solution is 0, 0, 0. That is always a solution, but that's irrelevant. The question is that, are there any other ones? And there aren't, and therefore S is linearly independent. Here's some straightforward facts. If you have a vector space and you have 2 subsets and one is inside the other, S is inside T, so every element of S is also an element of T. Then if S is linearly dependent, if the small one is linearly dependent, then the bigger one is automatically linearly dependent also. Why? Well, because if S is linearly dependent, that means some linear combination of elements in S is 0. Those same elements are in T, so that same linear combination is still 0 in T. If you want the other elements of T, the ones that were not in S, you can just give them all zeros as scalars, and you will still get 0. So if you can find some linear combination of elements of S equals 0, you certainly will be able to find some linear combinations of elements of T equals 0 also. The counterpositive of that is that if T is linearly independent, if the big one is linearly independent, then so is the small one. This follows from the first one by proof by contradiction. So we say, assume T is linearly independent. Why is S linearly independent? Well, by proof by contradiction, assume that S was not independent, was dependent. But by the first argument, if S is dependent, then that means T is linearly dependent, but we knew T was linearly independent, and that was a contradiction, meaning that our assumption that S is linearly dependent was incorrect, so S must have been independent. Here's another curious fact. If S happens to contain the 0 vector, then it's automatically dependent. The 0 vector ruins any set. As soon as you've got the 0 vector in there, it can't possibly be dependent. This is very different than, for example, when we were trying to find whether something is a subspace or not, and it had to include the 0 vector. If a set contains the 0 vector, it's automatically linearly dependent. Why? Because if you have the 0 vector, you can find a linear combination of just itself equal to 0 without using all the scalar 0. You can say 5 times the 0 vector is 0. There's a scalar multiple times that vector equals the 0 vector without that scalar being 0. So even this, if the set S contains just the 0 vector, it's linearly dependent. If you have one vector in your set, just V, and that vector is not the 0 vector, then it's independent. Because if V is not 0, if alpha V is equal to 0, then alpha must be 0. And if you have 2 vectors, then when is it linearly dependent? If you have 2 vectors, well, you're writing them as a linear combination equal to 0. That's true if and only if one of the 2 vectors is a scalar multiple of the other. So these are pretty straightforward facts. Now, a more interesting theorem, a theorem that we use quite often. If V is a vector space, And if you have a set S, and this is the set that you're wondering, is it dependent or independent, linearly dependent or independent, but you list it in a particular order. Now, usually sets don't have order. For this theorem and for a number of other things in linear algebra, we like our things to be ordered. So this is an ordered set, a set in which the order is fixed once for all. Let's assume that the first one is not the zero vector. Then the conclusion is that S is linearly dependent if and only if at least one of the vectors of S is a linear combination of the ones before. Now that word before is important because it has something to do with this order. So the question is that, is V2 a linear combination of V1? Is V3 a linear combination of V1 and V2? Is V4 a linear combination of V1, V2, and V3, and so forth? If the answer to any one of those is yes, then S is linearly dependent. If the answer to all of those is no, S is linearly independent. This is an if and only if theorem. So before we start on the proof, let me say just a couple of words about what that means. So we statement S is linearly dependent. Let's call that statement A. We have another statement B, that at least one of the vectors of S is a linear combination of the ones before. These are two statements. Neither one of them is always true or always false. The theorem is not telling us that A or B are true or false. What the theorem is telling us is that A is true if and only if B is true. The way we write that is with this if and only if sign. A if and only if B. This double arrow thing is a notation for A if and only if B. To prove such a thing, we have to prove actually two different things. We first prove that A implies B. That means that we assume that A is true, the statement A is actually true, and then we prove that B is true. When we are doing that, sometimes we just put in parentheses and a double arrow with the double arrow to one side to show that we're going from A to B. So when you're doing that, you can assume A is true and then use that to prove that B is true. And then we prove B implies A. In this proof, we can't use anything we used in the previous proof because now our assumptions are very different than before. Now we're assuming B is the true statement. Anything that we proved in the first part of the proof cannot be used now. So again, here we assume B is true, then we prove that A is true. If we do succeed in proving A is true if and only if B, then we have also proved automatically, without having to do it, that A is false if and only if B is false. Why is that? Well, because if A was false, but then B was true, then from what we had proved before, if B is true, then A is true, but A was false, so B must have been false, and the other way around. So if you prove A is true if and only if B is true, then you've also proved that A is false if and only if B is false. If and only if statements are important for us because they're characterizations. That means that we can actually use this as the definition if we wanted, because whenever this statement is true is exactly the same time as what the set is linearly dependent. So now let's go for the proof. I'm going to now prove one direction, the direction that we are assuming that the set is linearly dependent, and we want to prove one of the vectors in this order is a linear combination of the ones before. What does linear dependence mean? Because it's S linearly dependent, that means that we've got some scalars alpha 1 through alpha n, and not all of them are 0. And the linear combination of alpha 1 v1 plus alpha 2 v2 all the way to alpha n vn is the 0 vector. Now, what we want to show is that one of the vectors is a linear combination of the ones before. The temptation is to say, well, okay, which one? Well, maybe the last one, because Vn, I can maybe solve here for Vn and get Vn equals in terms of the previous one. The problem is this is sort of a little technical problem in the proof, but nevertheless, if you don't take care of it, then your proof won't be quite a proof, is that alpha n might be the 0 scalar, in which case if it's 0 scalar, then that term is really not there, and therefore you can't solve for Vn. So to solve that technicality, we start with this idea. We say that let I be the largest integer such that alpha I is not 0. So between 1, 2 through n, we said that not all of them are 0, so at least one of them is non-zero, but go to the last one that's non-zero. And if that's the case, then that means that everything after I, like alpha I plus 1, alpha I plus 2, and so on, were all 0. And so what we really have is alpha 1 v1 plus alpha 2 v2 all the way till alpha I vi equals 0. Because again, I was the last integer where alpha I was non-zero. After that, everything is 0. Now that we know alpha I is not 0, we can solve for vi. We can take vi to one side and solve for vi. And also note that I has to be greater than 1. It can't be the first one, because if alpha 1 was the last scalar that was non-zero, that means that we had alpha 1 v1 equals to 0. But then that would have been v1 is 0, and we had assumed that the first vector is not the 0 vector. Solving for vi, we take everything to the other side, divide by alpha I, and we get this. So what we got is one of the vectors as a linear combination of the ones before, and that's what we wanted to prove. We wanted to prove that if we have linear independence, then one of the vectors is a linear combination of not all the other ones, but just the ones before it, and that's what exactly we proved. Now we want to prove the other direction. This time we can't use anything we just proved. We still have the v1 through vn, but we don't know anymore that it's linearly dependent. In fact, we want to prove that it's linearly dependent. What we do know is that one of them, vi, between 2 and n, again, it can't be the first one because the first one can't be a linear combination of the ones before because there's nothing before it. Assume vi for one of those is a linear combination of the ones before. Now we have to show that S is linearly dependent. What we know is that vi is a linear combination of the ones before. Well, we can bring it to the other side, and when we bring it to the other side, we can also add on vi plus 1 and vn and so forth, and give them scalar zeros. And so our original equation becomes alpha 1 v1 plus alpha 2 v2 all the way till alpha I minus 1 vi minus 1 minus vi plus 0 vi plus 1 all the way till 0 vn equals the 0 vector. And now what we have is a linear combination of elements of S equal to 0. Moreover, we know that not all of the scalars are 0. Why? Well, because one of them is minus 1. The coefficient of vi is minus 1, and that's not 0. So that tells us that S is linearly dependent according to the definition of linear dependence. And so now we're done with the proof. And from now on, whenever we want to prove something is linearly dependent or independent, we can use this statement. This was if and only if. So it means that it's linearly dependent if any one of them is a linear combination of the ones before, and it's linearly independent if the first one is not the 0 vector, if none of the rest are a linear combination of the ones before. So let's look at an example. So this was the example we looked at before. Is S linearly independent? That's what we showed before that it was. Our new method is v1 the 0 vector? No, it's not. Is v2 a scalar multiple of v1? Can I take v1 multiplied by a scalar and get the second one? No. Is v3 a linear combination of v1 and v2? Now this one we have to think a little bit, but we can say that if it was, then if v3 was alpha v1 plus beta v2, somehow v3 has x and x squared. And somehow when we find a linear combination of those, we have to get that x and that x squared. The only way we can get x is by v1. And so the coefficient of v1 must be 1. Alpha must be 1 for us to get 1 plus x. For the same reasoning, beta must be 1 because we need to get an x squared. But if alpha and beta are 1, then we get v1 plus v2, and v1 plus v2 is really not v3. It's 2 plus x squared. And so we see that v3 is not a linear combination of v1 and v2. And so the answer to all of those questions is no. And so now we have that S is linearly independent. Unlike the original way that we solved it, we really did not have to do a system of equations or anything like it. So here's another example. These are our 4 vectors in R5, and I want to know if they're linearly dependent or independent. These are in some order. I could do the old procedure, write a linear combination equal to 0, see if all the scalars must be 0 or not. That would be the old procedure. I could do the new procedure by going through and saying, is the first one the 0 vector? Is everyone a linear combination of the ones before? But if I'm going to do that, I have to note that I can do that with any order that I like. So I get to choose the order. And sometimes if you change the order, things might be a little bit easier. The question is S linearly independent or not? I'm going to reorder S first. And I'm going to say, well, this is the order that I want. I'm going to write V2 first, V4 second, V3 third, and V1 last. Then I'm going to ask my set of questions. Is V2 the 0 vector? No, it's not. Okay, good. Is V4 a scalar multiple of V2? Can I multiply V2 by something and get V4? And the answer is no. If you want to make that 5 into a minus 4, you have to multiply V2 by minus 4/5. But if you do that
in the last coordinate and multiply -4/5 by -3, you're not going to get 7. So the answer to that is no also. Now, is V3 a linear combination of V2 and V4? Definitely not, because V3 has a 1 in a coordinate that V2 and V4 do not. And so there's no way to combine V2 and V4 and get that 1 in the second coordinate of V3. So the answer to that is no. Is V1 a linear combination of the previous 3 ones? And the answer to that is also an immediate no, because that first coordinate of V1 is a 4, and all of the other ones have a 0 in that coordinate. So the answer to that is also no. So as you have noticed, there was really no calculation to be done. All of those were quick decisions that we had to make, and therefore S is linearly independent, because the answer to all of those things was no. And this sort of illustrates that sometimes it is beneficial to use this theorem to decide linear independence as opposed to the original definition. So I want to finish with 2 slides about proof strategies. Whenever you want to do proofs, before jumping into trying to prove something, and then proof is not like some magical way of writing things, it's just a logical argument that tells us why what the thing that you're saying makes sense and follows from our assumptions. But before writing a proof, you want to always devise a strategy. You want to think ahead and say, okay, I'm assuming this is what I'm going to do. What always you want to do is start at the end, at what you want to prove, not at what you know. So you start by, what do I want to prove? And then you say, well, how do you prove such a thing? Without getting your hands dirty and actually proving it, you want to say, well, how do I prove that? Usually the answer to that question is either a definition that will tell you what that thing is and what you need to prove, or a theorem that tells you that if you know X or Y or Z, then you know the thing that you want to know. So you want to know your theorems and your definitions so as to be able to use them to do the proof. It's only then that you start using the things that you do know. Now, along the way, you might have to decide that the strategy didn't work, because there's no way to know a priori what a strategy exactly is going to work. So for example, if a W walks through the door and you want to prove that it's a subspace of something, then there's several strategies. You could say, well, W being a subspace of V means that W is a vector space itself. And so I could just use the definition of a vector space and go through all the axioms of a vector space and see that they satisfy. You would have to do that if W was sitting in an unknown set that you weren't sure that it was a vector space. For example, it had weird addition and scalar multiplication. And so you would have to actually show that V is a vector space, as well as maybe W is the subspace of it. But if W is sitting in a well-known vector space V, then you could use a theorem that says, in that case, all you need to do is check 3 things. The other things are inherited from V, that it contains the 0 vector, is closed under addition, and closed under scalar multiplication. A third method is to find a set S in W that spans W. So if you can show that W is the span of S, then it's automatically a subspace, because spans are always subspaces. So these are 3 different strategies that you need to pick prior to getting going. I mean, as I said, you might have to change along the way, but and decide that, well, that didn't work, so let's just go back to the drawing board and start over again. But at any given time, you need to know which strategy you're using. If you're trying to prove that the span of a set is W, how do we do that? Well, we basically have one strategy for that. We first must make sure that S is actually in W, and then we have to show that every element of W is a linear combination of elements of S. Finally, how do we prove that S is linearly independent? We have 2 strategies for that. One is the definition, right? A linear combination of elements equal to 0, show all the scalars must be 0. That's what we did originally. That's what the definition is. Or we can use our latest theorem that showed that the first element is not 0 and every other element is not a linear combination of the ones before. And again, implicit in that is that you're putting your set S in some particular order. This is the end of this lecture. We'll see you at the next lecture.